Hello, so today we'll be going through path planning algorithms in robotics. We'll be talking about the A-star algorithm as in comparison to the D-star algorithm. We will be talking about what RRT is. We will also be covering hybrid A-star for autonomous navigation. So let's get right into it. So first of all, here's a challenge. So we need to understand how a robot navigates from point A to point B while looking for safety, trying to be as efficient as possible, and updating the route in real time. To do that, we will be comparing the algorithms with static and dynamic obstacles. As the name suggests, a few of these obstacles are going to be fixed. In comparison, there is also going to be obstacles that are moving and are dynamic, for instance, pedestrians. And then there's also going to be real-time constraints, so the robot will be forced to make real-time decisions while moving, and then there will be optimality versus speed. Now, what is path planning? Path planning is basically a process of finding a collision-free trajectory from a start configuration to a goal, and is subject to a robot's kinematic and environmental constraints. So, for instance, autonomous vehicles, they, as the name suggests, rely on softwares and can perform tasks with minimal manual input. So, for instance, might it be changing of lanes, parking, highway merging, or anything else. There's also other types of robots such as aerial drones, which rely on software and path planning to perform maneuvers and to ensure that the drone reaches the place safely. And then there's our classic warehouse robots, which perform multiple operations such as lifting things, moving stuff from one place to other place, and to clean things. So now let's talk about the A-star algorithm, which is basically an optimal graph search with heuristic guidance. So as you see the formula here, it says Fn equals to Gn plus h of n, which is basically cost so far versus the estimated cost of the goal. So A-star algorithm guarantees that it finds a path if one exists, but it does so while finding an optimal shortest path. So it might be efficient as looking at the picture for the robot to follow a path of this sort, but based on the A-star algorithm, it automatically ensures that the shortest path is selected for the robot to travel, which in this case would be this path showed here. Here's D-star and D-star Lite algorithm, which is basically used for dynamic replanning for changing environments. For instance, there being an interference of some sort. So how this algorithm works is basically it performs an incremental search, which basically reuses the previous search results and ensures that there is no rerunning of the previous search. And then it performs a backward search, which is to basically look from the goal to the point that we are standing at to ensure that the shortest path is being followed. And then there's real-time planning, which basically means if there were to be any obstacle in the path, all of a sudden it performs the search again, but instead of it planning everything again, it just looks at the point that it's standing at and then tries to reconfigure the path to ensure that you avoid hitting anything. This is also the algorithm that's used in Tesla and other automated driving systems. Now let's talk about the RRT algorithm, which basically means rapidly exploring random tree. As the name suggests, it performs random sampling, which is to basically explore things at random points. For instance, if it travels from point A to point B here, it then performs a search to see if the closest path to the ending point follows in that direction. If that's true, it then tries to go to that point and then perform the same thing again. If not, it just keeps following till it finds the closest path. Now, in terms of probability, you will find a given path in enough time, but there's no optimality, meaning you're not going to be able to find the shortest path, but you will definitely find the path that's going to make sure that you reach things. Now there's the hybrid A star, which is basically motion constrained. search for real vehicles. So basically what it does is it continuously states, unlike A star, each node stores X, Y, and Z coordinates, continuous position heading angle, vehicle kinematics, respects turning radius, steering angle limit, and non-holonomic constraints of a car like robots, and it performs smooth paths, produces drivable trajectories that a real vehicle can follow without post-processing. So Tesla uses the combination of D star and A star to ensure that you get the best out of autonomous driving. So for instance here, the algorithm also checks for it respects the vehicle's kinematics, which basically means it also ensures that there is time and space given, also the turning radius given according to the vehicle's configuration. So at the end, here's an algorithmic comparison to find the best algorithm for pathfinding. So in terms of completeness, almost A star and D star Lite perform the same, just to basically be able to find the path to the end goal. RRT is probabilistic, meaning if there were not to be 100% of obstacles, or if the path is not to be blocked, it will eventually turncate into it finding the path. And hybrid A is more practical, which is basically real-time changes. It goes and finds the path nonetheless. Now in terms of optimality, A star and D star perform the same, so basically optimal, but RRT is suboptimal given the fact that it needs to constantly change its direction and other things. Hybrid A is near optimal as it turncates into it finding a path, but there not being a guarantee of it. Finding the best way to turn. Dynamic environment, A star has no dynamic routing, which basically means it just finds a path and tries to follow it, and if there were to be any obstacle thrown in the way, unless and until there is a touch sensor configured, it might end up in a crash. D star Lite, as the name suggests, it's dynamic, so of course it makes dynamic turns and stuff. RRT is limited. It can't truly stop if there were to be a thing thrown in front of it. Hybrid A star, the same thing. And then dim scalability, it's low for A star and D star. RRT extremely high, as it is also able to control the arms and other things, and this is something that it's mainly used for. Hybrid A, it's pretty good, medium 3D. Time complexity, O b to the power of D, pretty bad. D star amortized, same thing. O of N for RRT, which is really bad, and hybrid b to the power of D. Okay, for path smoothness, it's grid aligned, so is D star. RRT is jacked, and hybrid A star is smooth curves. So it really depends on your use case, and if you were to implement something for a car, I would prefer going for hybrid A star. But if it's just a robot that picks things up and doesn't really require smooth turns and can make sharp turns, then of course A star or D star would perform the same, as compared to RRT, which is not really the best way for you to move around a warehouse. And of course the use cases here, best for static grids, D star for dynamic maps, RRT for robot arms, and hybrid A star for self-driving, which is of course self-explanatory. Now here's the simulation and the behavior. So comparing all the algorithmic outputs, we see how A star performs as compared to D star, as compared to RRT, as compared to hybrid A. So key observations are A star is grid optimal but is angular, meaning there is to be a sharp angular turn made here, and then it tries to follow a smooth path, although you see a lot of turns being made. D star adapts to the path on the fly, but there's also a huge angular change based on the obstacle. RRT, of course, there's a lot of angular changes as the algorithm works in that way. And then hybrid A star is the best way for you to move around if you were to have a smooth drive. Now here are the key takeaways before we end this. So basically, no one size fits all, which basically means each algorithm has its trade-offs: optimality, speed, dimensionality, and real-time performance. And the algorithms are to be used based on the use case. And the environment matters, of course. If it's a static environment, then algorithms such as A star and D star might perform better as that compared to RRT or hybrid A star. I'm sorry, not D star, but yeah, as compared to A star, as dynamic is basically specifically the algorithm that might be used in dynamic scenarios is D star. And then 2D versus high dimensional. Of course, if you were to use something that's in extreme high dimension, then the best case for you is to go for the RRT algorithm as that compared to the other ones. And then of course the hybrid approach wins because it's a modern system, combines planners. So it has both the functionality of A star and D star, which is to basically A star find the shortest path, D star to find the dynamic path, and it just combines both of them while maintaining a perfect reasoning for the vehicle standards and kinematics in order for it to make smooth turns and other things. And then this is just a random keynote from my side, which is basically AI is the future. So deep RL, neural planners, and learned heuristics are transforming classical algorithms into adaptive intelligent systems. And this is something that we need to be proud of and might be witnessing in the near future. You might see more advanced systems that might take over the algorithm, that might even generate algorithms that would indeed turncate into us having better robotics algorithms that can help us navigate and perform tasks. Thank you.